All right, today we're going to try and crack open one of the most extreme, most mysterious objects in the entire universe. We're talking about something so dense, it just completely breaks our understanding of what matter even is. The question sounds simple enough, but trust me, the answer could literally rewrite the physics textbooks. What are neutron stars really made of? Okay, so how do we even get one of these things? Well, it all starts with the death of a giant star. I mean, a really big one. It burns through its fuel, can't support itself anymore, and collapses under its own incredible weight. The result? A massive explosion, a supernova. But after all those cosmic fireworks are over, something gets left behind, a tiny, unbelievably crushed core. And that little remnant, that's where our mystery really kicks off. Now, to really get a feel for how absolutely insane this thing is, let's just imagine for a second, what if we could scoop up just one single teaspoon of its material? Yeah, that one tiny teaspoon, it would weigh 6 billion tons here on Earth. I mean, that is just a mind-bending number. And that's the kind of ultra-crushed, reality-defying matter we're diving into today. So welcome to the world of neutron stars. Think of them as the universe's ultimate pressure cookers. They're pretty much the densest things you can find, aside from black holes. The gravity is so powerful, it crushes matter to a point that creates conditions and maybe even totally new kinds of matter that you just can't find anywhere else. Right, so this is why we call it a riddle wrapped in gravity. This extreme pressure is forging stuff that literally can't exist anywhere else. So, what is actually in there? What's going on inside that core? Answering that has become, honestly, one of the biggest puzzles in all of modern physics. For decades, the answer seemed pretty straightforward. It was right there in the name. A neutron star must be made of, well, neutrons. The idea was that protons and electrons get mashed together so hard, they just become neutrons. You end up with this giant, city-sized atomic nucleus. A simple, elegant theory that, as it's turning out, might be totally wrong. So to get to the bottom of this, physicists have a tool. It's called the equation of state, or EOS for short. Now that sounds complicated, but you can just think of it like a compressibility score for matter. It's basically the physics rulebook that tells you how squishy or how stiff something is when you put it under pressure. A pillow is soft, a diamond is super stiff. Same idea. And here's why this rulebook is so important. It should tell us something really specific. For any given mass, a neutron star should have an exact predictable size, or radius. It's supposed to be a clear relationship. But the story is getting way more complicated. Our observations from deep space are starting to suggest that maybe our rulebook is completely wrong. All right, so this is exactly where the evidence starts to not fit the theory. The mystery really deepens here because we're living in a golden age of astronomy. Our cosmic detectives are out there gathering all these clues, and they just don't line up with the old, simple story. And who are these detectives? Well, we have some incredible tools at our disposal. There's NASA's NICER telescope, parked right on the International Space Station, measuring the sizes of these stars with mind-blowing precision. And then we have gravitational wave observatories, like LIGO. These things can actually hear the ripples in space-time when two neutron stars collide. It's like getting a peek inside the crash itself. So this really gets to the heart of the problem. On one hand, we have the rules, the theory, that predicts this nice, clean relationship between a star's mass and its size. But on the other hand, we have the clues, the actual observations. And they're all over the place. We are finding stars that are way too heavy, or way too light, or weirdly small. They just don't fit the models. The theory and the evidence are clashing big time. So let's open up some of these impossible case files. First up, you've got PSR J0740 plus 662. This is the heavyweight champion, pushing the absolute limit of how massive a neutron star can even be. Then there's this other one, HJ1731347, which is just weirdly light and small. And of course, the big one, GW170817. That was the collision of two neutron stars that gave us so much data that no single simple theory could make sense of it all. Okay, so whenever your theory doesn't match what you're actually seeing, it probably means something else is going on, something deeper. And in this case, it means something exotic might be happening inside these stars. So it's time to bring in the usual or unusual suspects. And this right here, this is the question that's driving a whole revolution in astrophysics right now. If it's not just a simple ball of neutrons in there, then what else could possibly be hiding in that core? Okay, suspect number 1, Hyperon Matter. What are hyperons? Well, just think of them as heavier, more exotic cousins of the protons and neutrons we all know. They contain these things called strange quarks. And if these guys show up in the star's core, they actually make the matter softer, which means it's easier to compress. And that could be the reason we're seeing some of these stars that are smaller than they should be. All right, suspect number 2 takes things a step further. And it's pretty wild. We're talking about quark matter. The idea is that the pressure gets so immense, so completely off the charts, that even the neutrons can't handle it. They literally break down, dissolving into a soupy sea of their most fundamental parts, quarks. We're not just talking about a mix of particles here. This is a true phase transition. It's like the way carbon under pressure turns into a diamond. So, that leads us naturally to our third suspect, the hybrid star. Maybe it's not an all-or-nothing deal. This model suggests you could have a star that's kind of both. A normal outer layer, a crust made of regular neutron star stuff, but then a core made of that exotic quark matter. A lot of scientists think these hybrid models are really strong contenders for explaining some of the weirdest stars we've seen. And for our last suspect, we have the most mind-bending idea yet, the two-family scenario. What if? What if we're not even looking at one type of thing? This theory suggests there could actually be two totally separate populations out there. You've got your normal neutron stars, and then you've got a second family of even denser objects called strange quark stars. Two different species living side by side in the cosmos. So, we've got our lineup of exotic suspects. The big question is, how do we figure out which one is the real culprit, or if any of them are? Well, scientists are working on it right now, trying to crack this cosmic code. And the process is really just classic scientific detective work, broken down into 3 steps. First, the theorists come up with a new rulebook, a new equation of state for one of the suspects, like, say, quark matter. Second, they run the numbers and calculate what the mass and radius of a star should look like, if that rulebook is true. And third, and this is the most important part, they compare their prediction to the actual evidence, the real data we're getting from our telescopes. And the results? Well, they're starting to point in a pretty clear direction. There was this huge review of all the evidence, and I want to quote it directly. It said that modern observations seem to favor the existence of some type of exotic matter in the neutron star cores. What that really means is the old school, simple model of just neutrons, it just doesn't work anymore. It can't explain what we're actually seeing out there. But hold on, the final verdict isn't in just yet. We've got some really strong clues, and we have some very compelling suspects. But for now, the case remains open. You know, this hunt for clues has really been picking up speed. It all started back in 1967 with the first discovery of a pulsar. Then, fast forward to 2017, and we get game-changing data from both NICER and the first neutron star merger. Our view of these things is getting clearer and clearer, and the next big breakthrough might be right around the corner. There's a new facility expected to come online in 2026 that could give us our best data ever on hyperons. You remember, one of our main suspects? And all of this leaves us with one last, really incredible thought. These neutron star cores, they're nature's ultimate laboratories. They prove that if you apply enough pressure, the fundamental rules of matter can actually change. And it just makes you wonder, right? What other cosmic secrets are floating out there in the dark, just waiting for the right conditions to be crushed into existence?